Okay, thank you very much. Got the morning shift again, and it's all good. So today I'll talk about something a bit more esoteric, and essentially it's going to be a brief introduction to an area, very brief, and then I'm going to have three examples in order. So that pretty much divides things into three nicely. So if you fall asleep or zone out, you can re-engage when the next one begins, right? It's kind of minimize your loss. This is going to focus on something I call the evolutionary Nash program. What do I mean by that? Why do I say that? Well, the Nash program is a name that's been given to work that links non-cooperative game theory to cooperative game theory. I'm going to allow you roughly to figure out roughly what cooperative game theory is by giving you the three extended examples / papers later on. Essentially, it connects those things. The evolutionary Nash program just replaces non-cooperative game theory with evolutionary game theory. So if you think of cooperative game theory as a part of the theory of social choice, the evolutionary Nash program links evolution to that via dynamic models of cooperative games. Again, as we said yesterday, understanding solution concepts, in this case, cooperative solution concepts, although the gap between cooperative solution concepts and non-cooperative isn't perhaps conceptually so big, right? But in terms of the processes that can lead to them. Okay, that's good. That's good. We're on time. So this is the first example we have. It's matching. So there's a literature on matching. So let me describe a marriage problem, the marriage problem, which is a famous and well-studied problem in matching. So you have a set of men. You can do workers and firms if you want, but I think initially it's men and women. Set of men, M1 to MK, so a finite set, and a finite set of women, W1 to WL, and players. So if I use N, it's just for the set of players, which is all the men and all the women together. And there's going to be matchings. Basically, men are going to be matched to women. There's another problem where anybody can be matched to anyone, which is known as the roommate problem. That has, maybe stable matchings don't exist in that problem. But here we'll deal with the marriage problem, where you always get stable matchings as long as people have strict preferences. So matching is going to be an undirected bipartite network, by which I mean you have the set of men and the set of women, and a matching is a set of lines that go from men to women. Yeah. Now, we assume monogamy, right? So otherwise it's a many-to-one matching, otherwise known as the college admissions problem. So we're going to assume monogamy, so that each player is matched to at most one other player, but could be unmatched. And GI is going to be used to mean the partner of player I at a given matching G. So at this matching, G of M1 equals W2, and G of W2 equals M1. G of M2, well, M2 is unmatched, so G of M2 is the empty set, indicating that man number 2 is single at this matching. before I get onto this, this is not a game. This is not a non-cooperative game. It looks like one, but let me explain what I'm representing by these numbers in a second, please. They can be different or they can be the same, but yeah. Of course, if it's different, then one side of the market is guaranteed to have some singletons at any matching. So, right, so each player is going to get some level of utility, of payoff, UIG, from a match. But when I say from a match, they're only going to get utility from their own partner. Right? That's an assumption. In reality, you can assume models where people care about their friends, like the quality of their friend's spouse as well. Or you could have a model where people are envious, right? Don't want other people they know to have a good spouse or even to be matched at all. But in the classic setup, they've only got their own partner who they care about. So if you're matched to the same person at matchings G and G dash, then you're equally happy. Your payoff is the same at those matchings. And we're also going to assume strict preferences over partners, which means if your partner is different at matching G and G dash, then you get a different payoff. Right? So you're never indifferent between any two people on the other side of the market. If I say, oh, that doesn't work very well. I'll keep my hand away from there. If I ask a man, what do you think of these two women? Could you rank them? He can always say that one is better than the other from his perspective, right? And people can have different preferences, right? People don't need to agree on the ordering of partners on the other side of the market. Right. So for this problem, when I'm writing this, I'm using this to mean that when man 1 is matched to woman 1, man 1 gets a payoff of 8, and woman 1 gets a payoff of 2. So these are actually people who will be matched together. They're not strategies. That's the difference to looking at non-cooperative games. So if man 1's matched to woman 1, man 1 gets 8, woman 1 gets 2, and so on and so forth, and assume a payoff of 0 when unmatched, just to keep things easy for this example, which we're drawing here. Great. And so a matching, we've defined the problem, right? We've defined the problem. And you can say when a matching is stable. So what does it mean for a matching to be stable? A matching is stable if there are no two players such that who are matched to one another at G. So G is stable if there's no players who are matched to one another at G. So you see J is the partner of I, such that I prefers to be single and matched to J. So there are no people who are together where one of them would rather be single than matched to the other one, right? Because that wouldn't be stable because they could leave. The second condition is there are no I and J who prefer one another to their partners at G. Yeah? Because if they preferred one another to their partners at G, they could leave their partners and match together themselves. You'll notice, by the way, that if we compare this to, say, a Nash equilibrium stability concept, Nash equilibrium is talking about individual deviations, its robustness to one player changing their strategy. Every single player doesn't want to change on their own, conditional on what other players are doing. The difference here is this is a pairwise condition, right? It's not, so you need to be robust to possibly two match players pairing up. So two players leaving their spouses and getting together. Obviously, that's not something that one of them could do on their own, right? Okay. So let's, so its notation S here stands for stable, and it's the set of stable matchings within the set of possible matchings.
Just a quick
Yes.
You are including the constraint that two men cannot connect with each other, right?
Yes, absolutely. Yeah, basically two men or two women have no, like, they can't partner with each other, right? So it's just ruled out by the game. Or equivalently, they're just getting a very low, like minus infinity payoff or something for doing that. You can change that. That's absolutely fine. And there's a literature on the roommate problem as well. This case, this is just a marriage problem because it's the simplest to explain and because it guarantees that we're going to have stable matching, at least one stable matching. So in this example on the right, there are two stable matchings. There's going to be, which I've drawn here by different types of line. So one of the stable matchings is when M1 is matched to W1 and M2 is matched to W2. So that is, you're kind of getting these payoffs and these payoffs. Now, nobody wants to leave their partner to become unmatched because they get a payoff of 0. Does anybody want to get together with anyone else? Well, let's say, well, M1 is currently with his favorite partner, so he's clearly not going to leave. Can W1 leave and get together with M2? She'd like to, right? However, M2 is not willing to run off with W1 because he currently prefers his current partner, W2, to W1. And you can check that for, well, this matching as well, that matching as well. They are, well, this holds. There are no IJ who prefer one another to their partners. But there's also another stable matching. And you see that first stable matching is pretty good for men. They're getting their favorite partners. There's another stable matching, GW. I've indexed them like this for a reason, which is where M1's, this is the dashed line, matched to W2, and M2's matched to W1. Now, that's also stable. In that case, the women are getting their favorite partner, and any man, even though he'd prefer to be with the other woman, can't, because the woman doesn't want to be with him. She prefers her current partner. So we've got these two stable matchings, and I've called them GM and GW because GM is what's often called the man optimal matching. It's the stable matching that's best for men, best for one side of the market, and GW is a matching that's best for women, the other side of the market. If you have a bigger matching problem, so if we have more people, you could have more stable matchings. But it's not something I'm going to prove. There's a bunch of papers by Al Roth in the 80s, which are all very elegant and very short. It's back in the era where you were allowed to write short papers and in economics. So those papers have a lot of the results, most of the results on this literature, and of most of the old classic results. Now you have, in any matching problem, even if you've got much more men, many more women, you've always got a stable matching that's best for men out of all the stable matchings, and a stable matching that's best for women out of all the stable matchings. And in between, you can have other stable matchings. And these matchings actually have, the stable matchings have a lattice structure. So you can take joins of stable matchings and create other stable matchings. Anyway, some of you will, of course, already know that. I've got this problem. I'll just define this. This is similar to what we saw yesterday about talking about rules again. The set of Rawlsian stable matchings as, well, I was going to say, no, I think someone had defined it before me, probably. It's just too obvious a thing. But here, it's this, within the set of stable matchings, choosing the stable matching that makes the least well-off person as well-off as possible, treating utilities as cardinal and comparable. So the stable matchings that maximize the lowest payoffs amongst all players. So in this case, the Rawlsian stable matching is actually the GW, this one, the one where the women get their preferred partners. And the reason is in the other stable matching, in the man-optimal stable matching, woman 1 is very unhappy, right? Okay, so far so good. So let's consider dynamics in these matching problems, right? And, question. In this, it's not going to. In terms of, so there's a famous algorithm, the deferred acceptance algorithm, which is, the old joke is that if you ever read a matching paper, you know the answer is going to be deferred acceptance. And that's because it's, or some version of deferred acceptance. And that's an algorithm based on having one side of the market like ask for partners, their favored partners, and get matched tentatively, and then you work through it and you select a stable matching. And you are correct that by ordering it that way, you're going to select the man optimal or the woman's optimal stable matching, depending on who is proposing. So that's correct. But that's an algorithm that you can run for matching, and then you get an answer, and then you stick with the answer. In this case, it's not going to matter because we're going to throw a dynamic like the ones we looked at in the second session yesterday at it, which is going to have, well, it's going to be invariant and ergodic. And so where we start isn't going to matter in the Markov chain that we're about to construct. So we're going to just put a process on this matching problem. So let's take the state space being the state space. So yeah, state space being the, I haven't been drinking, I promise. So the state space is the set of matchings, and we're going to have a very simple dynamic that, well, the unperturbed version is originally due to Roth and van der Waait, where they were thinking, can we get to a stable matching through a reasonable process? A man and a woman meet, and if they are currently matched to one another, they consider separating, basically. Oh, should we separate? If one of them wants to separate because they prefer it to being together, then they separate. If at least one of them accepts separation, you can't force someone to be with you. It doesn't require them both to agree to a divorce. Otherwise, they consider leaving their existing partners and matching with one another. So if they're not already together, they say, hey, should we get together? And then if both of them accept it, then they get together. So then the question is, when do both accept, or when do you leave? Okay, so here's a case where you see man 1 and woman 1 have just met, and they're thinking, should we leave? Well, currently man 1's matched to woman 2, and they're thinking about whether to get together. Oh, man 1 prefers woman 1 to woman 2, right? So he's probably thinking yes, but woman 1's currently single and getting 0, so she should be thinking yes as well, right? They should be getting together. This is a case where woman 1 is considering accepting a bad man from her perspective, getting 2, rather than being single. Anyway, what type of dynamic are we going to do? Well, yesterday we spoke of things that could take place with some events that would take place, transitions that would take place with.
The way you're describing is like a one-shot situation. Whether they both accept, then they match. If one accepts, one rejects.
Then they still might split up the next day. It keeps going forever.
There's no ordering.
There's no happiness. No, there's no ordering. No, there's no, it's not like a finite number of steps or anything like that. There's no ordering. Let's just randomly choose a man and a woman to meet every period, right? You're all running about, randomly bumping into one another. And yeah, obviously not realistic, but it is simple.
So if one man and one woman meet, both of them are matched already, and if both of them want to separate only, then the new matching happens, right?
It depends if they prefer to be together than be separate. Like if both of them prefer being together with this person they bumped into to whatever their current situation is, whether it's being single or whether they already have a partner. If both of them prefer being together with each other to their current situation, then they may match.
What if only one of them prefers, the other one is fine with staying in the current match?
No, well, then we have no kidnap. Well, I mean, actually, I mean, in the kind of unperturbed dynamic world of perfect decisions, we have no kidnapping, right? In this here, we have mistakes or what should we say, random utility, stuff like this, right? So we're going to have noisy decision-making again, and in that case, one of them, even if it's a worse option than currently, they may take it. Again, that can be people making mistakes, or it could be, so you could have a random utility model where you've got your basic utility and you perturb it by adding, well, your payoffs are just different from day to day. Like most days you like a certain type of person, and then some days you wake up and you just really like women with red hair or something, right? Like because you watched a Nicole Kidman movie and your preferences are temporarily changed and it causes you to make some bad decisions. You're looking at me, you're like, yeah, bad decisions sounds like a good idea. But no, that's not. Anyway, so from a state, faced with the prospect, so you're at a given matching and you're thinking about moving to this other matching because you bumped into someone, this player will accept it with high probability. So that's going to mean of order 1, so not something that disappears with epsilon, if they gain from it. So if they prefer the possible new matching to the old one, right? So if they prefer their possible new partner or being single to the old one, they accept if they prefer their possible new partner. Or with probability, if it's bad for them, like you said, if it's possibly getting together with someone who's worse than your current partner, or worse than being single if you're currently single, you accept it with a probability. Well, again, this class of models we looked at yesterday, epsilon to the something that depends on the payoff from the current matching and the payoff from this new possible matching. So that could be a rule that, for example, says it could be the more you lose from making the mistake, the less likely you are to make the mistake. Briefly, because we're just sketching this model here, we're going to consider condition-dependent noise, which is you're more likely to do something wrong that's not good for your payoffs if your current payoff is low than if it's high. So your behavior gets more noisy and unpredictable when you currently have a low payoff. This is what it says here. It says, considering situations where your current payoff in one situation is u and your current payoff in another situation is u dash. If you use more than u dash, then this is bigger than this. But that means, of course, because it's epsilon to the power of things, epsilon to the power of something bigger is a smaller number. So you're less likely, well, I've written it here, you're less likely to accept a detrimental change when your current payoffs are higher. Under condition-dependent noise. There's a reason I'm describing it to you. So for sets M and W, we let U, big curly U, be the set of all possible utilities they could have. so numbers. And we let SS denote the set of stochastically stable matchings we looked at yesterday. As we let epsilon get small, where does stationary probability under the stationary distribution concentrate? And we have the following result. If behavior is condition dependent, so if you're more likely to make mistakes when your payoffs are low, then for all possible utilities you could have, your stochastically stable outcomes are a subset of your Rawlsian stable matchings. Maybe it's kind of it's intuitively unsurprising because you're more likely to make mistakes when your payoffs are low. So that works against the selection of stable states where somebody's getting a low payoff, right? There's still work to do, of course, because you require after, let's say you've got, in the example we looked at before, there was the woman getting a payoff of 2 in the man-optimal stable matching. Now, she was unhappy. She would be likely to make mistakes. Not mistakes, well, okay, let's say she'd be likely to make non-pairwise best responses. But once she's done that, you need to be able to find a path to a new stable matching, right? So actually leaving your existing stable matching is only half the job. But it turns out that with marriage problems, because of the nice structure of marriage problems, you can find, once you leave a stable matching, and let's say there's another stable matching over there, but once you leave, you can find a path of pairwise best responses, so with no mistakes, that takes you closer to that. You might bump into another stable matching on the way, that's fine, you've bumped into another one, but you are closer to some kind of target. And you can leave where you originally were. It's not that one, because in some games, problems, of course, one mistake is not enough, right? You have a form of evolutionary stability, and you get sucked back into where you started. Not the case here. This next one is, if behavior is not condition dependent, then there exists some payoffs that we could give the players such that the stochastically stable state is not Rawlsian stable. So for this particular result, that was the interesting thing for me, was getting a reverse result, saying that, well, almost an if and only if. Because once you've done that, you've kind of axiomatized the Rawlsian stable matchings in terms of behavioral rules, that if we have the behavioral rule condition dependence, it takes you to the Rawlsian stable matching, well, selects it under stochastic stability. But if behavior is not condition dependent, there's some game where it doesn't. So you're really drawing links between those two things. And I, probably a minority sport, but I quite like the idea of that, right? The idea of not just going in one direction and saying, if you behave this way, this is what happens. I mean, I do like that, but there's something nice in being able to say, if I behave in such a way, this is what happens. If people behave in such a way, this is what happens. But if they don't behave in that way, maybe something different happens, right? It's possible that something different happens. So the only way to guarantee that we get to here is to have them behave in that way. Another way to put it.
In the point 2, the intersection of the two sets can be non-null. And there can be stochastic stable states which are also belonging.
Yeah, I mean, if we think of a case where there's a unique stable matching, for example, that would be if there was only one stable matching, so this would be a case where the man-optimal and woman-optimal stable matchings were the same. Easy to think of one like that. Imagine there's 2 men, one who's great and all the women love, and one who's terrible and all the women don't like him. And then there's 2 women, one who's great and all the men love, and one who's terrible and all the men don't like them. And then obviously the stable matching, assume no one wants to be single, will be the 2 great people together and the two not so great people together, and there'll only be one stable matching, right? Basically, if you have a lot of assortativity, if people agree, the more people agree on preferences, the more you're kind of shrinking, in some sense, the set of stable matchings. Because if people roughly agree on the orderings, then the people who are high up the orderings of men and women get together, and so on. But yes, back to your question, if there's only one stable matching, then of course it would be the Rawlsian stable matching, and so you could have another perturbed pairwise best response dynamic. For example, you could have something based on logit, or based on probit, or based on uniform mistakes, and that would also take you to the Rawlsian stable matching, because there'd only be one stable matching, which would be Rawlsian stable. Yeah. So that's why it's written in this kind of two-point way rather than one line of if and only if. You can't, it's like you can't guarantee you get here unless you have condition-dependent rule, but for some preferences, you will get here anyway. So we did an axiomatization. How did we do that? That's right. That's right. It's the probability of erroneous choice decreases in your current payoff, but it's not a function, and that's only a function of your current payoff. It's not a function of your current payoff and the other thing. If a conditional on making an erroneous choice, it's not depending on the gap. It's not depending on the size of your mistake. It's depending on how happy you are currently. If you do a kind of logit version of pairwise best response, then you select a set of stable matchings that's like a matching version of something called the least core, which is a cooperative game theory concept. Basically, you'll see later, assuming we get to it. Otherwise, you won't see later. So, and you can ask me later. But yes, you can select other interesting things. Different rule. Anyway, so to leave a stable matching, the reason I did this is it's very clean and easy to explain this mapping, this from the condition dependence to Rawlsianism. So we have stable matching, which requires some player to accept a change that leads to a lower payoff. That's required to leave a stable matching. Now, under condition dependence, it's easier to accept such a change when your current payoffs are low. And that makes Rawlsian stable matchings the stable matchings that are hardest to leave with a first mistake. And that's one thing I call one-shot stability. There are other one-shot stabilities out there in the past, but in this case, this literature is this. It's the ones that are hardest to leave with the first mistake. Now, then the results from that, a co-author showed a few years back, that in this type of matching problem, stochastically stable matchings are contained within one-shot stable matchings. And that involves showing that those paths from close to one stable matching can go in the direction of a target stable matching, which isn't completely trivial, because imagine we've got some kind of space and we've made some distance between stable matchings, and I want to move over there once I've left this stable matching, but it could be that the easiest way to escape from here moves in the wrong direction. So then you need to do some work to show that there's a path that dances around your previous stable matching and heads off in the direction you would like to go. Anyway, that's a short introduction to that. Let's have a look at bargaining solutions. Lots of pictures. So take a breath, take 10 seconds. This is separate, this is different. These are some people sharing a pie, by the way. It's bargaining, they're sharing a pie. This is a bargaining frontier. So most of this section is going to be visual. It's a bargaining frontier. What does it show us? Well, it's the classic bargaining problem that Nash came up with when he wasn't doing Nash equilibrium. He did some work on bargaining problems, which is different. So you've got players alpha and beta here, and there's a bargaining frontier. Now what does this line show? Well, when the players bargain, they can reach a point inside this bargaining frontier or on the frontier. It's basically the list of things they can agree on is inside this set. And the frontier is the edge of this set. And this is kind of how much beta gets, or how happy beta is with whatever they agree with. And this is how happy alpha is with whatever they agree on. So you see the best possible point that for alpha would be to agree on this point here, where he got small s bar, big alpha, which is the most that player alpha can get out of that bargaining. And then on there, we've got s bar beta, which is the most beta could get. They're very successful in this bargaining. And then you've got all of this frontier between them, this line, is all of the Pareto efficient allocations that they could agree on. Everything inside here is inefficient, because obviously they'd rather agree on this, on the frontier, than this. So it's like a space of utility. And this frontier is given by a function, f. So if t is what alpha's getting, and you're on the frontier, then f of t is what beta is getting. So this function is f of t. Because assuming the players stay on the frontier, you can say what beta gets as a function of what alpha gets. Is that clear for everyone? Move on? Okay, seems good enough.
Could you explain why the curve should have that particular curvature?
Well, it's nice if this is a convex set. Basically, that's it's nice if it's a convex set. Otherwise, some of the classic bargaining solutions don't really work.
So this we are taking as a given thing.
Yes.
Okay.
Yeah. So we're given a frontier like this, we're going to discretize it. So we're just taking points on the frontier, because I want to operate on a discrete space. That's just what I'm telling you. It's just what I want to do. So I discretize it, and then I've got points like T4, f of T4, T5, f of T5. So you agreed. I've discretized it, and I've taken these payoff pairs from the frontier. And then I put them all in a non-cooperative game matrix. What type of non-cooperative game matrix am I putting them in? Well, I'm putting them in one where the bargaining frontier payoffs are on this diagonal. So we're going from player beta getting everything along the frontier payoffs all the way until player alpha gets everything. And so I've created a two-player coordination game. And off this main diagonal is just zeros. If they miscoordinate, they get nothing. Why am I doing this? Well, I'm starting with this object, this bargaining game, which is basically that. Okay, what can I do with it? I want to run some kind of dynamic process on it. But for that, I need objects on which I can run a dynamic process. And so one way to do this is to turn it into a non-cooperative game and then have people have, well, these these numbers, these parts from discretization, 0, 1, 2, 3, 4, as their strategies. So it's like they're agreeing on a point on the frontier, and if they don't agree, they get 0. Okay, one question there. Any?
Does person A know that person B, like what person B wants or how person B feels about what they're proposing? Like, do they have mutual information?
This is very deep. No, do they have? The information they know is what they use. So we're going to give you a rule that's like a best response rule. So there's basically going to be two populations who are going to meet people from the other population to bargain every so often. So there's going to be, say, like buyers and sellers, right? Landlords and renters, and every so often they're going to meet, and they do use the information about what the other side of the market has done. So yes, that's what they're going to use. Knowledge is always interesting in game theory, right? Because you can look at a model, and you can ask, what do players know? And you're like, what does it really mean to know? As one friend of mine said when I was, I don't know, complaining about something, he said, it's a bit like asking, like, does the apple know the laws of physics as it falls to the ground? And that sounds like a silly question to ask, but when you look at models of behavior, right, sometimes there's information that's used that is, I mean, it's encoded in different ways, right? It can be used explicitly by the players, or it could be information that's encoded in who they're meeting, when they're meeting. So just recently, somebody told me off. They said, the dynamic you're using requires too much information. Yeah, it requires too much information. It's an unrealistic dynamic. And do you know what dynamic it was? It was replicator dynamic. It was replicator dynamic. And you think, well, hang on, how can replicator dynamic need too much information? It's just, if you're successful, you're reproducing yourself, and there's going to be more of you. This doesn't require much information about, he said you need information about everyone's payoffs. However, if you were to, I thought about it, eventually, charitably, and thought, well, yeah, if you were to lock everybody in a room, and then you're saying, we're all locked in little cubicles, and then you have to give us information so that we update our strategies in some way to mimic the replicator dynamic in terms of how we're updating our strategies. Yeah, it's quite a lot of information, right? We're going to need to know how well we're doing relative to average payoffs of everybody else to choose a probability with which we update our strategy, right? So even things that sometimes seem very low information, once you change the story that you're using them in, can actually seem high information. So there you go. Anyway, it was charitable of whoever it was writing an anonymous report to think I invented the replicator dynamic. Let's keep going. So, we're going to consider two populations, alpha and beta. Each population has size n, so they're going to have equal sizes. Could be the same population, you just play different roles sometimes, right? Sometimes you're a buyer, sometimes you're a seller. A state is going to be the strategies for every player, as we've looked at before. And the strategies are these 0 all the way up to however many you have in your discretization. And the periods are t equals 1, 2. We're going to run it as before. Now, a player who updates at time t is going to play a perturbed best response, as yesterday, to the mixture given by the shares of strategies in the other population at time t minus 1. Again, this takes us back to the first lecture yesterday where we're saying, okay, mixtures can be understood as facing a population. I don't know who I'm going to play, but I know the shares. So I kind of know the probability with which I'd be likely to face a given strategy from the person I match with in the other population. let's consider 4 types of perturbations that vary on 2 dimensions, right? 2 dimensions. Most people would sell you 1 dimension. I'm selling you 2 dimension for free. So we have uniform versus logit errors. We've already seen these. Those are, remember, uniform was every perturbation is just epsilon. Logit was perturbations epsilon to payoff loss. And we're also going to have this extra dimension, less used. Unintentional means just no change, same. You can make any mistake. Intentional is the truncation of the distribution of perturbations so that you never ask for less than your best response. Unperturbed dynamic is best response, but you can be perturbed, like we said, that noise, mistakes, random utility. But in the unintentional, you can do anything due to that. In intentional, you're only ever going to ask for more, right? You never, when you make a mistake that's not a best response, it's only asking for more. It's never asking for less. So for player beta, it would always be biased towards a low number here. Strategy, when he made a mistake, it'd go down. And for player alpha, it'd go in the other direction. For example, if an alpha player's best response is strategy 4, then under intentional perturbations, he might play strategy 5 as a non-best response, but he'll never play strategy 3. Is this reasonable? Well, when you look at people in the lab, it's kind of what they actually do. So, I mean, whether it's reasonable or not, it's worth taking a look at. Theoretically, unintentional perturbations favor big transitions. For example, the players were at some convention, so perhaps they were all coordinating on, say, this point on 5, T5 and F of T5. And there can be big transitions where, say, some alpha players demand nothing by mistake, right? By mistake, they just say, okay, I don't care. I don't mind. And then if enough of them do that, then it becomes a best response for beta players to demand everything. Of course, that's not, these endpoints aren't stable because getting nothing, I mean, the other guys are asking for everything. Should I ask for nothing, or should I just ask for anything? By some guys demanding nothing and other players best responding by demanding everything, then you can hop from there. You can find a path of best response to wherever you want to go. It's kind of, can get a bit chaotic. Once you've got to close to the edges, you can go wherever you target. And because there's this, it's important to the dynamic to have people demanding nothing and then players saying, hey, some of those guys want nothing. If I ask for everything, I have some chance of getting it. There's some chance. Maybe I should do that. And because of that, these maximum values, the most you can get, actually matters because it's like a temptation. If I see the other side asking for nothing, some of the people on the other side asking for nothing, the temptation is bigger when my maximum payoff is bigger, right? Because I could get up to that maximum payoff if I matched with those people. However, if, to the contrary, if you had, well, on the contrary, on the other hand, if we have intentional mistakes, that favors small transitions because if alpha players demand a little bit more, it's easier for beta players to say, well, okay, I'll accept that, you know, I'll move to that instead, than it is if they demand a lot more, right? If there's a large demand, it takes more perturbations of alpha players demanding a lot more to convince beta players to switch than it does when alpha players are demanding a little bit more. But what it means when you're dealing with small transitions is it means the slope of your bargaining frontier matters, right? Why am I telling you this? Well, there happen to be bargaining solutions that are defined using these things. So there's some classic bargaining solutions that depend on these things. So the Nash bargaining solution depends on the slope of your bargaining frontier. The Kalai-Smorodinsky bargaining solution depends on the maximum values that people can get, the maximum amount of surplus. In addition here, we have logit. When we have logit perturbations, they favor perturbations by those currently receiving low payoffs. Why? Because they've got less to lose, effectively. Miscoordination hurts people on low payoffs relatively less. They lose less. Going to miscoordinating, you get 0. If you're already on a low payoff, by miscoordinating, you lose less than if you're on a high payoff. And so these ingredients, once we throw them all in, once we kind of like do some algebra, we find that the stochastically stable states under these dynamics approximate, meaning if we let our discretization become more and more discrete, more and more chopped, more and more fine, we approximate the following bargaining solutions. So this is the result of, this all comes from basically 3 papers, one of which I'm on. And essentially with unintentional uniform perturbations, you get Kalai-Smorodinsky bargaining solution. Some of you may not know what that is. Let's describe it. So we've got this bargaining frontier here, and you see there's the maximum points here. If we draw a rectangle, and this is the disagreement point, that's the, if they don't, that's just the 0, 0 point. If we draw a rectangle coming out from the maximum amounts they can get, and then we draw a line between here, 0, 0, and this point of the rectangle, then where it intersects the bargaining frontier is the Kalai-Smorodinsky bargaining solution. And that's well known, and it happens to emerge under uniform unintentional perturbations. Under uniform intentional perturbations, depends on the slope, and you end up selecting the Nash bargaining solution, which maximizes the product of the 2 players' surplus. So in this case, it would be maximizing T multiplied by F of T. I haven't drawn Nash on here because it's a bit trickier to draw.
So here, when you say solutions, you still mean if you deviate, you lose, that kind of thing?
I mean, when I say solution, well, these are cooperative. Well, these are solutions of the bargaining problem, which say, if I give you a bargaining problem, we need to find a way to find a point. And so Kalai-Smorodinsky said, that's one way to find a point. And it satisfies some nice axioms. And Nash had some other axioms and proved that if those axioms are satisfied, those properties, you select another point, which depends on the slope of the frontier. And also Ehud Kalai, so without Smorodinsky, said, well, if we change, they were looking at properties that bargaining solutions satisfy. I won't go into this. I mean, this is a lecture could be given on that, but another time. There's Kalai on his own said, what about the egalitarian bargaining solution? So what if instead we just have a line that comes out at 45 degrees, this pink one, and there we take where that intersects the frontier. So that's just going to give each player the same, right? It's 45 degrees, you're increasing both players' utility the same. So you're going to have this T equals F of T point here. And that's the egalitarian bargaining solution, which happens to be selected when we run these dynamics under logit with intentional mistakes, intentional perturbations. And those are the big 3. When it comes to bargaining solutions, these 3 here really are the famous big 3. So, if you're not familiar with bargaining stuff, you can go on Wikipedia, you can read about them, you can read about the nice properties that they have. They differ in their properties, right? For example, you might want, if you stretch the bargaining frontier, you might want the solution to stretch with it. That'll be the case for some solutions, but not for others. So it's kind of nice that in this small world of perturbed best response dynamics, logit and uniform are well known, unintentional is well known, intentional is less used, but as I say, it turns out to be what people do in the lab, and also it's a very simple way to describe it, like truncate, truncate. So it's kind of nice that the three big bargaining solutions turn out to emerge from these dynamics. What's the logit BS, the logit bargaining solution, right? Well, that was new, and it's defined as what emerges in that thing, right? As coming from logit and unintentional. And it's actually can be quite weird and non-monotonic. I mean, for some parameterizations, it can be written in this way, which is like an equal loss solution, your TL here, which is like imagining this point, then letting each player take losses from that point equally until you hit the bargaining frontier. Now that sounds very intuitive, right? And that is a bargaining solution, the equal loss bargaining solution. However, there's something very weird and wacky here, which is usually if you're talking about equal loss, you're talking about a loss relative to your own maximum payoff. In this case, we're looking at player alpha's loss relative to player beta's maximum payoff, and player beta's loss relative to player alpha's maximum payoff, which is strange. But it's what comes out. I mean, logit is one of the most well-known things, and if you just throw logit at this problem, it's what emerges, which is kind of an indication that even when your ingredients are nice and easy to use, you can get weird things emerging, right? Because the other examples are like, we have nice ingredients, and we put them in the pan, and we get nice bargaining solutions coming out. But then just next to them, we have the kind of, like the bad sibling in some sense, which does some weird things. Anyway, the standard approach, just before we get onto that, the standard approach to bargaining solutions is to think of the properties that the solutions have. For example, most solutions satisfy symmetry. So they say if we had a bargaining set that's completely symmetric around the 45-degree line, so it's like the players are facing each other are equal, then you should choose a symmetric solution. You should choose something on the 45-degree line. They assume symmetry and efficiency as well, which is, choose something on the frontier. And then there are a variety of monotonicity conditions about how you would want your solution to change if you change the frontier. So for example, you might say, well, if we give a bigger frontier that comes out further, then both players should get more. Seems reasonable, right? Maybe I should draw it again to be a bit clearer. Like say if you had a couple of bargaining frontiers, perhaps if you had the second frontier, the solution to this one, or any solution you choose, should give both players more for this second frontier than from the last one. Because it's like you've got a bigger pie, so both people should have more. And for some, you can see for an egalitarian solution, that's obviously going to work because you're going to cross this one before you cross that one, and this point will give both players more than this. But if you've got something that depends on the slope, like the Nash bargaining solution, this may fail. right? You could end up with one player getting less even when you expand the bargaining frontier. And then there's different types of monotonicity that these satisfy. However, the important thing for now, for the comparison we're making, is that that's kind of like taking a normative approach. They say what properties are nice for a solution to have, right? What properties are nice? And then they say, it turns out that these nice properties are satisfied if and only if, well, satisfied for all bargaining problems, if and only if we use, for example, Nash bargaining solution, or if it's different properties, if and only if we use Kalais-Morodinski. So that's defining bargaining solutions according to what their properties are. But in contrast, what we have here is bargaining solutions, what would be the word, classified according to dynamics that give rise to them, which is a kind of different way of looking at why a bargaining solution might be good. Rather than saying it's a good solution because it chooses things that are like this, it's like it's a good solution because, well, it comes from a nice dynamic. So we took people into a lab to play this, so we did experiments on this, and because stochastic stability, often you've got arguments about time horizons, we just looked at how people behaved. Like, we wanted to see how people's perturbed behavior looked like. So first question was, did they usually best respond to the information we gave them? Here it's relevant, right? Because we're giving them information on the screen. And we're basically telling them, this is what the other side of the market did last period. These are what the average things they did were. And when we looked and we saw, did they best respond most of the time? The answer was yes, they did best respond. They did best respond most of the time. And then we could ask the question, when they don't best respond, what do they do? And the answer was, they depended on payoffs, so they were more like logit than they were uniform. And they were intentional. When it was a non-best response, it was usually asking for more rather than asking for less. So that would indicate that using a kind of logit payoff dependence error that's intentional, that indicates egalitarian solution as having a nice stability properties. So in a way, combining that empirical stuff with the theory gives some support for egalitarianism. Please.
Was the experiment done on like a specific group of people from somewhere? Because it could also be reflective of like cultural values and whatnot in terms of when they, think certain way, certain way.
It was done in Hong Kong, so whatever you think of Hong Kongers. I don't think Hong Kong is the most egalitarian place in the world, so maybe it's like a lower bound, right? But yes, it was done in Hong Kong on probably undergraduates. I have to check.
Where would you classify US-UK?
Well, do you want me to draw a bargaining frontier? I'm afraid I can't answer that question because 2 dimensions is not enough. Otherwise, I would be very happy to completely solve the issue for a fee. Yeah. No, that's all very, is what it is. Anyway, that's some bargaining stuff. Well, we have 20 minutes left, so we'll do a bit about. I'm just going to come to hear you. Okay, well, at the last place we had some bargaining frontiers.
So all the bargaining frontiers, they were actually smooth. So are you exploiting the the frontier, the function, it has to be non-differentiable, it has to be differentiable in some way?
As far as I can remember, yes. I mean, the bargaining solutions apply to non-smooth things as well, but in this case, for the Nash results, certainly we're using differentiability.
Okay, thank you.
Thank you. Okay, so let us move on. By the way, anytime I answer a question on some of these results, you have to be a little bit, because, you know, it could be something that I wrote several years ago. I mean, it probably is something I wrote several years ago, right? So, but no, we definitely do use differentiability there. So you can see that as a weakness. Right, so we have recontracting and the core. Let me describe a little more stuff to you quickly. Some of you, I said I'd kind of tell you what a cooperative game is in a few examples. So to some extent, matching problems that we saw are cooperative games, right? They're looking at not just individual strategy choice per se. You can't really give a strategy for an individual that makes sense independent of who he's matched to, and people are deciding together whether to get together or not. And the bargaining problem, seen as a cooperative game. And there's also, these are what's known as characteristic function form games. It's maybe the most classic type, which set of players, just like in a non-cooperative game, but we're not going to bother with anything. Well, we will, because we have to, but typically in the raw cooperative game, you don't have any strategies. You've just got this function that tells you how much surplus any subset of players, so S here, can generate. So Vs gives the value. Think of V as representing value that S can obtain and share amongst themselves. So we've got the whole population of, well, people, tomatoes, and they are sharing a pie. So perhaps this pie is the amount they can bake between all of them, and they want to share it. But you don't want to perhaps say these three, if they were just on their own, they could bake a pie of a certain size. So you don't want to give these three less than they could bake on their own, right? Because they're not going to come back, or they're going to reject the offer. They're going to say, we'd rather bake a pie on our own than accept this share of the pie that we're being offered. And you could say that for any subset of players, right? You could say this group, how much pie could they bake on their own? And if the answer is more than they're being offered by the grand coalition of everyone, then they say, no, thank you. You can put conditions on this V. It's usually assumed to be super additive, which means that, well, it means that these two tomatoes together with these two tomatoes, so it means all four tomatoes together can make at least as much as if you looked at two different sets of the two tomatoes, right? Because the worst you could do, imagine we formed a team, and we're like, what can we do with this team? And you guys would be like, we hate each other. And I'd be like, okay, so, but we can at least do as well by splitting the team into two sets, right? So that would be dividing it into S and T, but between all of us, we could do at least as well as that. That's super additivity. A stronger condition is convexity here. Because of time, I shall well, just say this is stronger than super additivity. It gives greater returns to scale when you're increasing the size of a set. Because you can imagine, usually it's typical that we could do at least as well as we could if we split up into smaller groups. Sometimes we could do better, right? Could be increasing returns to scale there. Right. The thing I just said about tomatoes not accepting pie, so that's that, basically. If all the tomatoes got together, does it help to talk about it in terms of tomatoes sharing a pie? Okay, seems it's a popular approach. So if we're D is sharing the pie amongst the tomatoes, amongst the human tomatoes. So everyone's doing that. This is a grand coalition. So we're saying if the grand coalition forms of everyone, all the tomatoes, and they share the pie, they create a pie which has size V of n, and then they share it amongst themselves in these proportions di, where I is the identity of a tomato. And the sum across all of the players equals the size of the pie. And then we have this constraint. If we add this constraint here that says no subset of players should get less than they could produce on their own. So if these constraints are satisfied, we've got what's known as the strict core of this game, this non-cooperative game, this characteristic form game. Strict because we've got a strict inequality here. So if your allocations are in the strict core, no coalition can improve upon payoffs given by this allocation. And the word feasible, D is feasible for a coalition if the coalition could create it on their own, right? So basically what this says is it says D is infeasible for a coalition, right? They couldn't do that well on their own by leaving the large group of people sitting at the table. The core is an important thing. It's it's not always empty under superadditivity. If you've got convexity of the characteristic function, then yes, it's always, sorry, it's not, it can be empty, right? The core can be empty even with superadditivity. If you have convexity of the characteristic function, it will be non-empty. Now, what can we do? We wanted to do some dynamics on this. Well, one thing I did once upon a time was say, well, let's create strategies, a bit like before. We moved from the bargaining game to a place where we could have strategies chosen by players. And you can do something similar here. And so for a player, I said the strategy should be a demand for a certain amount of pie. So it's, again, there's a discretization happening. But a strategy also isn't just a demand. It also says who I'm willing to be in a team with, who I'm willing to produce surplus with. So it's this subset of the player set. It's part of my strategy as well. So given strategies of all the players, you choose a feasible partition of the player set. And okay, what type of partition should we choose? We're calling it a feasible partition if D is feasible for S. So we've chosen a partition of us, of the tomatoes, and it should be that if there's a set of players in that partition, take V4 again, if we are in a set, our strategies should be, our demands should be satisfiable by this set we're in, right? Our V of us should be at least as big as what we're demanding. So if I demand 3, you demand 2, you demand 2, you demand 3, then that adds up to 10. So if we are set S, we need to have Vs at least equal to 10, right? Otherwise, we're not allowed to form. But also there's the condition that we should all accept one another as potential members of a coalition. So our set of acceptable coalition partners contains the other people in this cell of the partition of player set. And the same applies to any other groups of players that we're forming. Technical assumption there. Now, given this, you can you can specify payoffs. You can say that, so you've got the possible feasible partitions that could form given how much we're all demanding each, and given who we're willing to be in coalitions with. Now, you've got a bunch of possible partitions. We select one of those, the sum distribution, and given strategies and given the partition, we say that if we're part of a non-singleton in that partition, then we get our demand, right? Because we can get our demand, we have this satisfied, well, for whatever we're asking for. So we get our demand. Otherwise, we're not part of a non-singleton, we're just on our own. We just get like what we can make on our own. Okay, and we have the amount we can get our demand D. We have strictly increasing concave VNM utility UI over the amount we get. Right, so you'd have a UI of whatever DI you're getting, however much surplus you're getting. And so now we've kind of given a setup where we've taken our players that were in a cooperative game and we've mapped it to a more non-cooperative setting in that we've got strategies which are our DI and PI, so how much we're demanding and who we're willing to be friends with. And given everyone's strategies, we have this mapping that chooses a partition of the player set, which then tells us payoffs, right? Well, it gives us the demands, are they satisfied or not? I guess we'd call it allocation. The amount of surplus we get as based on demand. I guess I'll call it X here, and which gives us payoffs, right? Basically, your payoff is either going to be your utility of your demand, or it's going to be your utility of what you get on your own. Apologies for this slightly misplanning. Is that clear? Yeah. But so basically, the thing is we've created a non-cooperative setup from this cooperative game. We've at least created something where players have strategies that they can update as part of a process. So let's think about two possible processes. So this one is an individualistic process. So individual sample from the past m periods. So I look at what happened in the last m periods. I have a memory, length m. And then I best respond to my expectations that I form from sampling what people have done in the past, with some independence assumptions on there that we won't go into. And then I perturb my behavior in a uniform way. And then we get selection of a stable outcome. Well, we get selection of something in the core. So we get, if you let epsilon be 0, so you've got no perturbations, and people are just sampling the past and best responding, you converge to the core. And stochastically stable states solve this thing here, minimizing this maximum of this thing that involves utilities. But if all players have the same utility function, then what this essentially means is that stochastically stable states minimize the surplus of the wealthiest player. So you're kind of minimizing the wealth of the wealthiest player, conditional on being in the core. So you've got stability, and then you're minimizing the wealth of the wealthiest. Now this, well, having been asked about cricket, at least twice since I got here, and apologizing profusely, I should mention that this is kind of written in my way, but it's a result by a former colleague of mine, Murali Agastya, who yeah, asked me the same question about cricket many years ago. So this is one way of doing it. Now, one thing, okay, we have time. This setup here, it's individual updating in an individual dynamic. Each individual is best responding, even though the payoffs are generated collectively, right? Given my choice of demand, I'll be put in a set of players and we generate the payoffs and I get my demand. Or I don't get put in any set of players and I don't get my demand. So you've got an individualistic dynamic, but a kind of a kind of group-wise generation of payoff. Coalitions are generating payoffs. Why do I say this? Because I want to distinguish it from what if strategy updating was also done by coalitions? I want to distinguish generating payoffs as part of a coalition, which is where we're working in the same team and payoffs are coming from who we're in a team with affects the payoffs that are being generated. I want to distinguish that from choosing to change your strategy. This is individualistic. You can do it with a coalitional dynamic if you let any subset of us have a chance to get together and play a coalitional best response. So this is basically something that's as good for us as, well, we think would be the case if we just stayed doing the same thing, and also satisfies some kind of Pareto condition on what we're doing, keeping what everybody else is doing fixed. So you're allowing some kind of coalitional updating, and then you perturb that, then you get different selection, because coalitions can actually choose what they're doing. So we could get together and say, well, we're not currently part of the same team, but actually if we formed a team, we could do better than what other people are doing right now. And we can guarantee that team forms. That's the kind of little trick, little grain there. We could guarantee that our team forms by saying we will not accept being partners with anybody else, right? So that's why this part of the strategy helps, right? Because it means that you can guarantee you're part of some target team rather than just hoping that your demand might be satisfied by some possible partition. Anyway, if you run a coalitional dynamic on this, then you get different selection. So you're maximizing this, previously it was maximizing overall the players this term. Now you're maximizing the sum of the same thing over all players who aren't this player, which is easier to understand if you choose a specific type of utility function when it simplifies into the stochastically stable states are then the ones that maximize Rawlsian social welfare. I've chosen to give a lot of Rawls this conference, but essentially maximizing the payoff of the least well-off person. I mean, what this function, you're doing two things. It tries to minimize wealth inequality amongst everybody except the poorest person. You take the poorest person, you take them out, and you end up minimizing wealth inequality amongst everyone else, but at the same time, you want the poorest person to be kind of wealthier, right? So you want these guys to be as poor as possible, so you're making the poorest person wealthier to make everybody else as poor as possible, but at the same time, you want, while you're giving wealth to the poorest guy, you want these guys not to stretch too much. You want to keep them all not too unequal. And that comes from like an effect of the concave utility functions, right? But if you take this special case, it reduces to Rawlsianism. So a kind of cheap and cheerful banner headline would be individual dynamics on this type of setup minimize the wealth of the richest guy, whereas the coalitional dynamics maximize the wealth of the poorest guy. An interesting thing here, I only have 16 seconds, but this is in some of the other examples, I'm going to overrun by 30 seconds, sorry. if the, okay. Okay, great. Okay, 30 seconds. Some of the other examples I've given you, there's a possible criticism of assumptions being close to the results in the sense that you have a dynamic that depends on, say, payoffs, say depends on perturbations are more likely when you've got low payoffs, and lo and behold, that destabilizes outcomes where people have low payoffs, right? So you can say that those things are quite close together. That's not the case here, where the perturbations are just uniform. There's no payoff dependence in the perturbation setup at all. So the actual stability of this comes from the basic best response dynamic. Anyway, of course there is more, blah, 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 general behavior rules in matching, matching with transferable utility. That's where you can make that woman who's terribly unhappy to have married such a terrible person happier by transferring your utility to her. Robustness to coalitional behavior in general, coalitions and contagion, coalitions and poverty traps. In general, the question of how aspects of culture arise and persist, embodied in institutions and conventions. Also, we can look at the evolution of constraints themselves, individual constraints and collective constraints. The shape behavior. Okay, that's great. I'll do something completely different. Somebody cancelled, right? Which means I have an extra talk on Thursday, but I promise something completely different for then, if that's okay. It's still evolution. Thank you very much.
Just a quick one. Do any of these apply to organisms beyond human beings? Are there any experiments or observations?
Organisms beyond human beings. Yeah. So by beyond, you mean super intelligent AI that is coming next year, or no, I know what you mean. It's okay. I mean, do they even apply to human beings? Would be the, or is it just pure theory? No. I mean, it could do as long as you have something that looks like a best response and something that looks like. So I mean, mutation rates. I think there is evidence. I think some cases in biology where mutation rates are higher when there are worse situations, right? So that's where the kind of idea of condition dependence in errors comes from, or at least gets its backing. So, yeah, the general concepts.
No, I was thinking more in terms of cooperative games, like a group formation.
I don't know. Is my answer, right? I mean, I've done work with cooperative games and evolution in this theoretic sense, but I don't know about any geobiology literature on this type of stuff. It must be, right? It could be quite old, but you feel it must be. I mean, though, cooperative game theory is not very popular. So I remember when I was a PhD student, I won't name him, but a quite famous guy who was a professor at Harvard at the time came to give a talk. He says, "What are you doing?" And I said, "Well, you know, I'm thinking I could combine like evolutionary game theory and cooperative game theory. That could be quite interesting. I've got some results." And he just said, "You should work on something people are interested in." And that was it. So, right. I mean, there must be, right? Like group formation, coalition formation must have been studied in this. Yeah. Okay.